In this lecture, we are going to continue our exploration of machine learning-based trading. This lecture will consider the question, what if we plug in a super powerful classifier? If you've studied machine learning, you know that linear models are comparatively pretty weak. At the same time, this doesn't necessarily mean they aren't useful. However, it's worth trying a more powerful model just to see what happens. Recall my rule, all machine learning interfaces are the same. What this means is we can accomplish this with zero new code. All we need to do is plug in a different model. Okay, so let's start by importing the random forest classifier. As you know, the random forest is one of the best plug-and-play models for tabular data. This is because it combines the expressiveness of decision trees along with the variance reduction that we get from ensembling. Inside the constructor, we pass in random state equals 0. If you've studied random forests, then you know that there is some randomness inherent in the training process. Thus, if you don't include a random state, you will get a different result each time. This does not imply that you should use the random forest this way. This is just so that we get consistent results in this lecture. In the real world, you would want your model to be robust enough to work all the time, no matter the random state. Okay, so next, we call the usual functions model.fit and model.score. So we can see something very interesting. On the train set, we get a perfect score, 100%. On the test set, we still only do slightly better than chance. So random forests are very powerful, but they are so powerful that they might fit to the noise in your data. In this case, that's definitely happening. Okay, so next, we're going to call model.predict to get ptrain and ptest. Next, we assign the position column, based on ptrain and ptest, as usual. Next, we compute the algo return column, same as before. Next, we check the sum of the algo return column on the train set. Not unsurprisingly, it does extremely well, 4.7. This is because it's perfectly predicting all the ups and downs on the train set. So it's able to take advantage of all the ups and never experiences any of the downs. Of course, the test set may be a different story. So next, we check the sum of the algo return column on the test set. And we get about 33%. Let's print out the buy and hold results once again. So we see that the random forest greatly outperforms the buy and hold strategy for both train and test. Now remember, these results are only for this particular random seed. This does not imply that you can take this algorithm and go make $1 billion. Let's scroll back up and try random state equals 1. Okay, so as you can see, these results are not robust to the random state. We still get a perfect score on the train set, but now we underperform on the test set. Let's see what happens if we try random state equals 2. Okay, so again, we get a perfect score on the train set, but now on the test set, our return is even higher at 0.38. So there are lots of important ways that you have to test the robustness of your models. As you just saw, sometimes there's randomness in the model training process itself. There's also randomness in the data. The signals that were predictive 20 years ago or 10 years ago, or even 3 months ago, may not be predictive any longer. Remember that random forests are a very powerful model, but a model only works as well as the data you give it.